So the first thing we're going to do is we're going to talk about partial derivatives. A partial derivative is one component of what we're going to build up into the notion of a derivative. And the partial derivative just basically takes a function of several variables and measures what happens if we change one of the main input variables. So we change that one input and we leave the rest of the other inputs constant. So this type of notion works for real valued functions, ones that have a single output. And they still use a limit definition like we're used to. And they're very handy, and they're also very calculable based on the types of things we already know from single variable calculus. So if we have a real valued function, let's say we have a function of 3 variables, it's going to have 3 different partial derivatives. We can calculate the derivative that tells us what happens if we change x and leave y and z constant. We have one that tells us what happens if we change y and leave x and z constant, or we have one for telling us what happens if we change z and leave x and y constant. And so those give us 3 different partial derivatives: the x derivative, the y derivative, and the z derivative. And we write those in the following way: del f, del x, del f, del y, and del f, del z. So this is supposed to be similar to, but slightly different than, the notation for ordinary derivatives we use with df dx as the notation. I'm very possibly going to play a little fast and loose with the rules and forget that I'm supposed to write d or del sometimes because my brain doesn't come up with that very quickly. I apologize in advance if that happens. You may also see notations like this: d sub f of f, d sub x of f, d sub y of f, or d sub z of f, that tell us in kind of operator theoretic notation what's going on. And just as before, each of these partial derivatives changes. Depending on where you are, your function may be changing faster or slower. And so the partial derivative depends on the point you measure it at. So it's still going to be a function of 3 variables. And all of this goes through whether we have 3 variables or 4 variables or 5 variables or 2 variables or so on and so on. Now, there is a limit definition for partial derivatives. It's not going to be the main focus of the course, but it's still important to know that this is how it's calculated. So this limit definition is basically the same as the ordinary definition of a derivative. So we do f of x plus h minus f of x divided by h, but here at the bottom, we can see an example where we're calculating the partial derivative of f with respect to y, because I made a mistake in my slides. And the way we get it is we replace y with y plus h and leave the other variables alone. Like I said, we're leaving 2 variables constant, x and z, and we're seeing what happens when we change y. We calculate the derivative with respect to y alone. In terms of graphs, this interacts in a nice way with what we were doing when we were thinking about graphs of functions last time. So let's say we have a function of 2 variables, z equals f of x and y, and we want to know what the derivative of f with respect to the y variable is at a particular point, a comma b. So let's take a look at how we could think about that. The graph of this function is going to be some surface that lives over top with the z coordinate is equal to f of x, y. And if we fix a value of x, if we keep x constant, say x equals a, that gives us one of these sections. That gives us a section of this graph that looks kind of like this, and it turns it into a function of a single variable. That function of a single variable just has one input y and one output z because we've isolated out and said x is equal to a. And then within that, we've got an ordinary single variable graph of a function, and we're just calculating an ordinary derivative this way. So that's another way to think about it, is it's just kind of the slope if we just use a particular direction for the function.